Okay, so next talk is starting now. Benno van Berg is going to be talking on recent progress in the theory of effective current fibrations in simplicial sets.
Okay.
The online people can't hear any audio.
Can you hear me now? Ooh, I can hear myself
Yes,
as well.
thank you.
Is it fixed? Okay. The project is around trying to understand Vygotsky's model construction of type theory in simplicial sets from a constructive point of view. So this builds on many different things, including the so-called quant-Quillen model structure in simplicial sets. And if you look into the proofs, maybe I should also say that how are these two things related? Well, the model structure on simplicial sets that I'm interested in includes a class of fibrations, which are the so-called Kant fibrations, and these are the ones that are used in the model construction to interpret the dependent types. If you look at this, the proof of this, the proof of the existence of this model structure, the proof that Vygotsky gave, they will use classical logic and the axioms of choice actually in various places. So the question that was actually also of interest to many people in the community, I mean, it was also discussed, especially in Princeton, can all of this be avoided? So before I actually go into that question, let me just very briefly remind you of all these sort of important ingredients, and in particular about the basics of the theory of simplicial sets. So the simplicial sets is a presheaf category. It's a presheaf category on a category called delta, where the objects are finite, non-empty, linearly ordered sets, usually written by this square bracket n. And the morphisms in this category are monotone maps. Of special importance are two classes of maps, the so-called phase maps. So these are maps from square bracket n to square bracket n plus 1, which omit a certain element. And then there are the degeneracy maps, which are surjective maps from n plus 1 to n, which repeat a single element. In fact, you can write every object, every morphism in this category delta as a composition of these two maps. In fact, every map factors as a surjection followed by an injection. Every surjection can be written as a composition of degeneracy maps. Every injection as a composition of phase maps. And in fact, we can also prove that every surjection in this category delta splits. If we move to the presheaf category, so presheaves on this category delta. Then, of course, we have the representable presheaves, which are usually written like this and called the n simplices. And I will be interested also in subobjects of these representables. So subobjects of representables are usually called sieves. And we would like to think of these things as sort of like subcomplexes of the n simplex. So this could be delta, well, let's say delta 2. And then a subcomplex basically consists of selecting a number of points and the number of edges in this n simplex. Amongst these sieves, there are the so-called horns, which are which you obtain from the entire n simplex by just deleting the interior as well as one face. And if it is the face opposite the vertex with index k, then we call it the horn, kth horn, and we write it like this. Now we would like to think of the subobjects of delta n as subcomplexes of the n simplex. But if we do all this if we think about this more constructively, then actually that is not so clear. So what we really should be focusing on, I would think, is the so-called sieves for which the question whether, or like subcomplexes for which the question whether or not a certain vertex or a certain face belongs to the subcomplex or not is decidable, which is not generally the case in a constructive meta theory. But if this condition holds, I will call the sieve cofibrant. And I think it's really in the constructive context, the cofibrant sieves that we're really interested in. It's also the cofibrant sieves. I mean, we can only, for example, in general, we cannot prove that delta n has finitely many subobjects, but we can prove that it has finitely many cofibrant subobjects like this. Okay, this was already my first sort of constructive interlude. So the definition of a confibration is this. So here there's a map f from y to x is a confibration if it lifts against any horn inclusion. So here is this horn. Here are two maps, arbitrary maps, making it the square commutes. And if such a filler exists, we call it a confibration. And an object is called a concomplex if its unique map to the terminal object is a confibration. Now, I think the first thing to note is that in the classical theory, all of this is understood as properties. So a confibration is a map for which this thing does exist. Also, that I think is from a constructive point of view not such a terribly good idea. So I will, in a constructive context, it's much better to think of this as structure. So we could say that a map is a structured confibration if f from y to x is a structured confibration if for any such square I'm given an explicit a choice of a lift. So I said that this theory of Vovodsky's model and the existence of this Quillen model structure, all of this is uses the law of excludable and the axiom of choice at various places, but I mean, can this be avoided? Is there any sort of fundamental obstruction? And the answer is yes. So this was found by Besem, Coquin, and Parman, and one thing that they note is that the classical result, which says that a to the power b, so this is using the exponential in the category of simplicial sets, that this is a concomplex whenever a and b are, that result is not constructively valid, which is quite bad for us because this is how we want to interpret the function types in type theory. Note that the concomplexes are the intended interpretation of the types. So I will refer to this as the BCP obstruction. In fact, the classical proof doesn't even really need that B is a concomplex, but they're sort of, So this is basically, they already show that this sort of restricted version of that classical result already is not provable constructively. And in fact, this result can also be, Parman basically also observed that Also, you can't sort of solve this problem by switching from Kahn complexes to structured Kahn complexes, then this result is still not constructively provable. So how do we respond to this BCP obstruction? So I think there are three fundamental possible responses that you can find in the literature. So one is basically to switch to cubical sets. The other one is basically just to accept that this obstruction exists and just continue. And then the third possible response is to say that, well, maybe there's something wrong or with the definition of a Kahn fibration from a constructive point of view. Maybe it better be modified in some way. So what I will sort of look at this, mostly focus on this third possibility. So about cubical sets, maybe it's already good to notice that, I mean, the people who do cubical sets basically make two changes. So first of all, they switch to another proof-sheaf category. And the other thing is that they add uniformity conditions. So yeah, actually, and then of course the other question is which form of cubical sets do we take? Is the model of type theory that we get, or the model structure that we get, actually equivalent to spaces? Well, I mean, you should look at Evan Cavala's talk from HoTT from last week for a discussion of all of these questions. Okay. Then the other possibility is just to accept that this obstruction exists and continue. So somewhat surprisingly, Simon Henry has managed to show that actually using this notion of structured Kahn fibrations, you can still show that that exists a Kahn-Quillen model structure. Of course, this doesn't lead to a model of type theory. Well, I mean, there are some issues to which extent you can still claim to have a model of type theory, but in fact you can get quite far, although I would say you don't really get a model of type theory, not with the usual rules for these function types, of course. And then there are also some sort of coherence issues for which no solution is known. Then, of course, there's the other possibility of just say, well, let's mess with the notion of a Kahn fibration and basically maybe strengthen it in such a way that maybe these results become provable. There is a precursor for this, the so-called uniform Kahn fibrations, which in some sense were also present in Sina's talk. So the problem with that is that this notion is not local in a suitable sense, which means that we can't use the Hofmann-Streicher method to construct universes. So for that notion of Kahn fibrations, we don't really know how to construct universes. To motivate, okay, so this is very much something that we did together with Freek. So to motivate this definition of an effective Kahn fibration, so in the book we have many different definitions, some of them quite involved, but actually it can be boiled down to something very simple in the end. But for that, we basically first have to ask ourselves the following question. So suppose that you have a map, and I'm telling you that it is a structured Kahn fibration, so it has, we are given favorite fillers against horns. What other kinds of maps do we also have fillers against besides horns? Well, if I have a favorite filler of this map, if F has a favorite filler against G, and I have a certain other map over here, which is a push-out of G, I also have a favorite filler against this map, because, well, here's my favorite filler against G, and then using the universal property of the push-out, I get a filler here. So I also get favorite fillers against push-outs of horns. If I have two maps, G and H, and I have favorite fillers against those, then I also have a favorite filler, in some sense, against the composition of these two maps. So if I have like a square like this, then first I can take the composition here, and that gives me a favorite filler here, which makes everything commute. Then I have this square here, and I have a favorite filler there, which makes everything commute. So that basically means that if I have a sequence of maps, and I'm sort of told that, okay, here I can write this as a decomposition of things which are push-outs of Horn inclusions, in some sense I have a favored filler against that thing as well. So let's say that if I have a sequence of sieves on some delta n, and each of them is like a push-out of a Horn inclusion, I will call this thing a Horn push-out sequence. So basically what I'm saying is that if I'm given two cofibrant sieves S and T, and I'm sort of, I can write them as sort of the endpoints of a Horn push-out sequence, then I have a favored filler against that inclusion of sieves. One issue is that the way I can actually, the way I write it, or the way I decompose it as a sequence of maps which are push-outs of horns may not be unique. And it's not a priori clear that actually I will get the same filler for each possible decomposition. In fact, I suspect that's not the case. Okay. So, to motivate the definition of an effective confibration, let's wonder about the following questions. Suppose I have a horn here, and I pull it back, against a degeneracy map. What kind of map do I get here? Now, it turns out that, okay, this is not a horn. It's more stuff is missing. But this thing over here can be written as the composition of a sequence of maps, as a composition of sequence of maps, which each of them is actually a push-out of a horn. So basically, I can obtain delta m plus 1 from S by sequentially filling horns. This decomposition is not unique. However, you can argue that the induced, if I have a structured confibration, the induced lift against any structured confibration of this map over here will be the same. So this is our definition of an effective confibration. A structured confibration is an effective confibration if it has, of course, favored lifts against horns. And when I take this horn, and here's my favored lift, and I pull it back, I get this thing against which I also have a favored filler, which I can write over here, and then these two choices should be compatible. So this triangle here should commute. So this is the uniformity condition that we have for these effective confibrations. And yeah, so we have been showing many things for them. For example, first of all, closure under, so basically solve the BCP obstruction. In fact, we can show that these are stable under pi. We can construct all the other show closure for all the other type constructors as well. Importantly, the notion is in some sense classically correct, so we can prove in a classical matter theory that every confibration can be equipped with the structure of an effective confibration. We do know that we could construct universes using the Hofmann-Streicher construction. What I still do not know is whether these things are effectively con or satisfy univalence. How much more time do I have? 2 minutes. That's including questions. Oh, it's not included. Okay. Okay. So I have many more things. Maybe I'll just run through one thing. I'm working on a proof together also with Paul Seip and John Berg, and showing that these effective confibrations are the right class in an algebraic weak factorization system. We have a classical proof of this, but I mean the challenge would be to make this constructive. I'm fairly confident that that can be done. Eventually, the hope would be that we can actually get an algebraic model structure out of this. One interesting thing is that I don't expect these effective confibrations to be closed under retracts constructively. So this is a bit odd because then the definition of a model structure requires the fibrations to be closed under retracts. So it's not actually what I expect will happen in the end is that these effective confibrations are going to interpret the type dependencies and it is the retracts which are going to be the fibrations in the model structure. So these two things I would expect to be to diverge. And it might sound very strange, but actually I would like to remind people that actually in the groupwide model of Hofmann and Streicher, they actually use the split fibrations of groupoids to interpret the dependent types. Now, split fibrations of groupoids are not closed on the retracts. So also in that sense, you could say that what they use as their interpretations of dependent types is not exactly the same thing as what the fibrations in the model structure of groupoids. So that this is sort of to argue against the view that it has to be the case that the fibrations in the model structure have to be literally the same class of maps that will interpret the type dependencies. So I mean, these things could be the same. And if this project is successful, they will actually be sort of, will be this different when, so the class of maps in the model structure and the class of maps interpreting the dependent types will be different. So that's it. Yeah, thank you.
Questions? Yeah. There is a microphone.
Yeah, maybe just a clarification. At some point, you said that one of the approaches to overcome this obstruction would be to move to cubicle, but I thought the same obstruction exists for the cubicle sets if they're not changed, right?
Which problem to cubicle set with cubicle set are you referring to?
Go back to you said
the BCP obstruction. No.
Yeah, the BCP obstruction. Then you had a slide.
Yeah.
After this, say go cubicle. Yeah, next one. Yeah, and
yes.
now you say go cubicle, but it seems that going cubicle without uniformity is just the same as for.
You have this. You have the similar problems in. So this was also a point that has been made by Nicola Gambino at various points, that in some sense the BCP, the way the cubicle sets people sort of overcome the BCP obstruction is not really so much by switching to cubicle sets, but by adding uniformity conditions. Yeah. So if that's the point, then why not try that in simplicial sets?
Right, and that's what
I'm trying to do.
In the paper in general, I mean, for them, cubicle and simplicial are instances of this uniform version of Kahn fibrations.
True, yeah. So indeed, for their uniform Kahn fibrations, for the uniform Kahn fibrations in the paper by Gambino and Sattler, they also show that basically by adding at least certain uniformity conditions, you can overcome in simplicial sets. Also, you can overcome the BCP obstruction. Their problem is a different one, namely in the construction of universes.
Yes, as we know.
Yeah.
Okay.
More questions? So I actually had one. Do you have any special cases of univalence? So like in cubicle sets, so you kind of started by just saying, if you have an equivalent somewhere, then there's a path in the universe.
No. So what I've been trying to do, but basically what I'm trying to do is basically the equivalence extension property / gluing, a la basically in Sattler's paper. But the problem, I think, is that I can't sort of copy that proof literally. In fact, because it uses closure on the retracts of the fibrations. So that is going to bite us. So I think I have to go back to that at a moment when I have not too much to do, but because it's kind of tricky.
More questions? Okay, in that case, maybe let's thank Benno again.
Yep.